We often think of humanity as the big dog of Earth, but in truth, we are rather small as apex critters go. Could we be an abnormality, small in size, and could this be our big answer to the Fermi Paradox? Today we'll be looking at the Big Alien Theory, posed by astrophysicist Fergus Simpson, that explores the likelihood that Earth's human population is significantly larger than most other intelligent extraterrestrial civilizations. This perspective is grounded in statistical reasoning and the vastness of the universe, and so we will be dipping into some math today too, population distribution statistics. As usual, the math is just supplementary, and there's no pop quiz at the end of the episode. We're spending a lot of time talking about bigger brains specifically, though that's not part of the theory, and that theory is pretty straightforward. You presumably need some minimum physical size to be a naturally evolving critter able to discover or invent technology. Any size bigger than this is fine, but the bigger you are, the more resources the individual needs. Thus, the more scattered the population of those critters will be, fewer in number and not able to congregate as closely in those early city days. Food and supplies for the same population require a larger harvesting radius and transport time. An elephant herd or whale pod is going to have a heck of a time transitioning to something like the fertile river valley civilizations, where we start seeing a lot of engineering and recording going on. As such, there might not just be a minimum size for intelligence, but a maximum one as well. And overall, we would expect the folks on the lower end of that size scale to vastly outnumber the ones on the higher end, since they take a lot less food per person. If we imagine that we had 100 planets, each with a species whose average calorie needs were 1,000 calories a day, 2,000, 3,000, and so on, up to 100,000 calories a day, then that first planet could support 1 billion people at a certain level of technology. The next would only support half a billion, then a third of a billion, and that last, needing 100,000 calories a day, has only 10 million people, and if you're curious, that's about the calorie intake for an elephant. To get the total population of these 100 worlds, where the most populous had a billion, is just 1 billion plus half a billion plus a third of a billion, etc., which is a harmonic series and works out to be 5.19 billion. So almost a fifth of the folks live on that one planet and are tiny, with a 1,000 calorie per day limit. 44% live on those 5 planets with 1,000 to 5,000 calories per day, while less than 1% live on the 5 highest calorie planets. Simple example, but shows how you are more likely, if we assume you are random and normal, to be from one of the planets with smaller people. Moreover, you are likely to be from a planet that can support a larger total amount of life. All things being equal, a planet that is bigger can have more people or bigger food chains. Same as with physical size, there are limits to how big a planet can be and support life, and how small probably too. I'll note a bigger planet would generally have higher gravity, which might make being a bigger organism even harder, as well as harder to spare calories for large brains. Simpson goes through the Bayesian statistics, for which we are the only data point, to predict the average alien weighing around 300 kilograms or nearly 700 pounds, and that they on average come from a smaller planet than Earth. He took examples of various intelligent critters on Earth and used that to get the figure for average alien weight, dolphins, gorillas, elephants, and whales being pretty big. Though it is also justified by the idea that a bigger critter can support a bigger brain. Even if you can only use 1% of that brain for tasks related to deep thought, rather than motor control and processing sensory data, 1% of a larger brain is more deep thought than 1% of a smaller brain. While our knowledge of exoplanets skews heavily to bigger and hotter planets, them being easier to see, we do take for granted that there are way more smaller planets than bigger ones. It's more or less baked into the physics, and our own solar system seems to prove it. If you are a random particle or bit of mass, incidentally, in the solar system, there is a 99.8% chance you are in the Sun, and a 0.1% chance you are in Jupiter, and a 0.1% chance you are anywhere else in the solar system, which includes over 1 million minor planets, though you are still more likely than not to be in Saturn than everywhere else combined. But more importantly, it's a lot harder for a planet much bigger than ours, like Saturn, to realistically have a lot of dry land that can support life and not be crushed by its own weight. Indeed, you don't have to get much more massive than Earth before having surface land or even oceans gets improbable. Again, we wouldn't expect those on Saturn. So Earth, Simpson reasons, is on the large side for inhabited planets and humans on the small size for intelligent animals. Thus there are a lot more humans on Earth than aliens on the typical alien planet. We need less food than the typical intelligent alien and have a bigger planet to grow that food on. As a result, the most common type of alien planet out there is one that can support less food production while also needing more per alien critter. This makes it hard for them to hit the critical density to snowball into science and technology. So the galaxy has a decent number of intelligent critters out there, but they stick in early eras because they just can't afford to make larger towns or cities and civilizations for creating, preserving, and refining technology. Channel regulars can probably spot some good reasoning there, but also some flaws, and the argument is mostly statistical, which we are not going to delve into much. In addition, to discuss the strengths and weaknesses of the big alien theory, we will also be exploring what alien civilizations made of relative giants might be like, from those just a bit bigger than us to truly titanic aliens like the Zentradi from Robotech and Macross, or even the Celestials from Marvel Comics. Now, there are certain maximum size limits a creature on land, even a relatively low-gravity planet, would tend to have, though having some different natural skeleton material like aluminum or titanium instead of bone might help with that, but only to a point. The 5-mile-tall Celestials from the MCU are not evolving anywhere but deep space, not even deep seas. We won't be ignoring deep-sea megafauna, but as we explored in our episode on if you could get technology without fire, that's quite an uphill lift. Same when we looked at giant space monsters a couple years back or cosmic megafauna, most of the scenarios didn't tend to favor civilizations arising. It does permit those critters to exist though, much as a blue whale can, but probably not as a civilization. Before we dig into the details though, we need two big caveats. First, a big alien might not be a natural one. The Celestials certainly are not, and those Zentradi from Robotech, for instance, are the product of a precursor civilization engineering them that was using them as their expansion and defense force. Even without assuming a post-biological civilization, deliberate engineering, especially in space where gravity is off the table, can let you get much bigger. Indeed, the Dysonian librarians of the epic novel House of Suns pursue a path of longevity that involves always growing a little bit bigger every year to add new brain cells and end up as giants in zero-gravity spaceships. That's also the fate of Bean, the mutant supergenius from Orson Scott Card's Enderverse novels, who was a product of genetic engineering. And on the less intentional end, humans are a good deal bigger than our precursors. Australopithecus was much shorter and about half our weight, and we see a general size increase as we get closer to modern humans, with even Neanderthals being shorter, if denser in bone and muscle mass we believe. Size is expensive and requires more and more effort to be given over to movement and having a skeleton that doesn't snap if you trip while running, not to mention longer maturation times, which will often imply a need for parents that protect their young for very protracted periods and necessarily have relatively few kids. Though emphasis is relatively, as humans have very, very long maturation periods even compared to the biggest organisms, with us equivalent to the blue whale, which also needs 20 to 30 years for full maturation and live about 70 to 90 years, but are a couple thousand times more massive than us. Their brains are several times bigger than ours too, though it is around a 10,000th their mass, compared to our own brain being about 2% of ours. This brings up the second caveat. A giant creature has way more body mass and energy to support a brain, so if their brain architecture allows a decent piece of that to be devoted to something other than sensory processing and motor control, they might be flat-out geniuses. And bigger critters live longer too, generally, and thus might be disproportionately likely to discover science and engineering even with a small population. A key notion of the big alien theory is that if you have bigger aliens on a planet, there are generally going to be less of them since they need more food, less people, lower density too, less likely to get specialist and technological advances. If they do have, on average, bigger brains, then they may also on average be smarter. Architecture and substrate matter more than size for brains, but size still helps. Moreover, we would expect their individual members to fall into a bell curve distribution of IQ, same as we do. Let's imagine three alien species here, the Typicalites, the Outlyrians, and the Brainiacs. Human IQ is a touchy and highly debated topic, and there's multiple scales, but the most commonly discussed tends to be the Wechsler Adult Intelligence Scale. And like most IQ scales, it asks tons of people tons of questions, then puts 100 as the score that half the people did better and half did worse than. And then it goes up and down in 15-point brackets in which an even tinier fraction exists. This produces that characteristic bell curve look, and lots of things chart this way. Not everything, and you can get double bump type effects, like if you charted human height, where you get a slight dip between the separate peaks for men and women. Or human weight, where there's a lot more folks 50 kilograms overweight than 50 kilograms underweight, for instance. Right skewed, so the curve is flatter on one side and has a long bulging tail on the other, and more than half is on one side of the peak. For IQ, most folks fit into those central to 15-point regions, 85 to 100 and 100 to 115. For Wechsler specifically is 34% for each, or a little over 2/3 combined, and anyone not in those two brackets is a bit of an outlier. The folks in those next two brackets, 70 to 85 and 115 to 130, each represent about 14% of the population, and a bit over 95% of those people are in those four brackets total, with just over 2% on each side, beyond those four main brackets. Most of that remainder is in the 55 to 70 or 130 to 145 range, with just 0.13%, a little over 1 in 1,000, in that 145 plus range. 160 plus is about 1 in 31,000. Incidentally, each of those 15-point brackets represents one sigma, or standard deviation from the mean, in this case 100. By our normal population distributions, for IQ and many other bell curve things, also called a normal distribution or a Gaussian distribution, and shows up in a lot of distributions not involving psychology, humans, or even biology. Again, plus or minus 1 sigma would be 68.27%, that first standard deviation. The second sigma, or standard deviation, will contain 95.45% of the population, the third sigma 99.7%, and this is the empirical rule of statistics, or 3SR, or the 68, 95, 99.7 rule, take your pick. And for each sigma, half is on the left or right, in this case dumber or smarter. You can keep going beyond this with more sigmas, but to be honest, especially with real and complex objects like people, your distributions rarely will match up well with what you'd expect, even if you get a big enough sample. You can use even things up into the 6 or 7 or 8 sigma or even higher in physics for stuff like how particles behave, but particles are very simple and very numerous and don't think or adapt. Something we're seeing today is how much a plant's conditions can affect what sort of animals evolve there and succeed. Our world has a vast and fascinating history, and Joe Scott's new Nebula documentary, Oldest Newest Places on Earth, we join him in exploring that as he travels from some of the oldest rock on the planet to lava that's creating brand new land. Many of you already know Joe's work. He and I have collaborated on a lot of projects over the years, including Nebula, the largest creator-owned streaming service, home to original, thoughtful content from us and many other great creators. You'll see every episode of SFIA premiere there early and ad-free, along with monthly exclusives like The Future of Interstellar Communication, where we explore how civilizations might stay in touch across light years without wormholes allowing fast conversations. Nebula is where I release a new exclusive episode like this every month, along with extended editions and other bonus content. Use my link with the QR code on screen to get 50% off our annual plan. Just $30 for the whole year, about $2.50 a month. Head to go.nebula.tv/IsaacArthur and start watching today. It's also worth remembering that intelligence is hardware and software, not magic, so a 9th sigma IQ does not necessarily imply that a person is much smarter than a 4th or 5th sigma. I wouldn't encourage folks to overly focus on IQ, but it is a handy number, and one that does tend to be genuinely useful for studying humans, even if it probably is an amalgamation of many loosely related brain and personality attributes that probably wouldn't translate to alien brains very well. Nonetheless, it has its uses and is familiar, so we'll use it for our 3 alien groups. Again, the typicalites, the Outlierians, and the Brainiacs. It is probably no shock that most science and inventions tends to come out of that 130 plus range, in spite of them being relatively few in number. Things tend to follow Price's law in that regard, but that's a side topic we won't dip into today. So our first aliens, the typicalites, have the same average intelligence as us, but they have a tighter distribution, 99% of their folks fall into that 85 to 115 range, rather than 2/3 like ours. So 115 IQ for them is just as smart as a 115 for us, but is as rare in them as a 145 IQ would be for us. A 115 is 3 sigma for them, and for simplicity we'll say every 5 points off 100 would be a sigma, rather than 15. They would then be way out at 6 sigma for 130 plus IQs, and 6 sigma have a frequency of about 1 in a billion, and would be an IQ of under 10 over 190 for us normally. But for them it's just those over 130 or under 70, so the pre-industrial typicalite civilization probably has at most one person of a 130 plus IQ around at a time, and often has stretches without anyone there. Since it took them an incredibly long time to progress technologically, even though they're just as smart on average as us, they had a very long pre-industrial time and a very large population over several million years, so they have had a few 7 sigma individuals born, but for them that was just IQ 135. They just never get a Da Vinci or Tesla or Einstein or anyone close. We estimate a bit over 100 billion humans have lived, most in the last couple millennia, in spite of us being around for around a million years. But the typicalites have been around for millions, and thus number in the trillions. Indeed, when they finally did discover concepts like radioisotope dating, they already had a recorded history of 2 million years to compare it to. On the flip side, the Outlierians have a way wider distribution. For them, 115 isn't 1 sigma, 120 is, and 140 is a second deviation, and 160 is third. They have the exact same IQ on average as humans or typicalites, but now 7% of the population has a 130 plus IQ, and a 160 plus IQ isn't a few dozen folks out of a million, like for us, or something that never happened, like for the typicalites. It's better than 1 in 1,000 of them, so the Outlierians progressed very quickly technologically. The Brainiacs are an interesting alternative as they are smarter on average than us. They come in at 115, but their deviation is the same as us, so they also have more 130 plus IQs than us or the Outlierians. But the Outlierians beat them on the frequency of really high IQ folks. It might be interesting to imagine which group, the Outlierians or the Brainiacs, would progress faster technologically, or imagine how that biology worked. The Outlierians might have no maximum size, just a brain that grew as they aged, so they almost inevitably turned into super geniuses with centuries of experience if they survived that long. Now, our topic today is about physical size more than brain size, but we need to understand that intelligence is always the key thing in discussing the Fermi Paradox, the big question of where all the aliens are, since at the moment we can't spot any non-technological civilizations, let alone planets covered in nothing more complex than lichen, even if they are around the nearest stars to us, or so common most stars had one. We also simply cannot divorce size from brain size, and thus to dig into big alien theory specifically, we have to begin with those caveats and notes about population distribution. Big alien theory begins with the observation that, within Earth's animal kingdom, humans are relatively ordinary mammals, distinguished primarily by our large brains. However, when considering intelligent life across the universe, humans represent just one of potentially countless species capable of contemplating existence beyond their own planet. Given the universe's immense scale, it's plausible that numerous intelligent species exist, each with varying population sizes. Nonetheless, the bigger the organism, by default, the smaller the population of them. Elephants just need a lot more land to live off of than humans, or a single mouse. To understand how humans might compare to these extraterrestrial civilizations, the theory employs statistical principles. We already noted that with IQ, but in general, individuals are more likely to possess common traits, such as prevalent blood types, than rare ones. Extending this logic, a person is more likely to be born in a country with a large population than in one with a small population. Of the roughly 200 nations on this planet, totaling a bit over 8 billion people at the moment, about half live in the top 10 most populous countries, around 5 and 6 in the top 50, while less than 1% live in the bottom 50, and that still includes pretty big countries. If your country has more than 30 million people in it, it is in the top 50 by the way. We used a parallel example earlier with our 100 planets, where most of the population came from the ones with the lowest calorie needs, which then had more people, and of course a random person picked from the 100 would most likely be from one of the low-calorie planets as a result. Same math reasoning here, just a real-world example. You are more likely to be from a populous country, and again, big alien theory also reasons that most life-bearing planets are smaller than ours, which again is probably valid. There should be more planets with 99% of our mass than 101%, and many more with 90% of our mass than 110%. Planetary mass distribution and star distribution is not a bell curve. It slumps off heavily as you get more massive. That said, I would be surprised if all those planets were equally habitable and productive on an acre-for-acre basis, so to speak. Bigger planets probably are oceanic and smaller ones lower on air and water, but given our limited real data on exoplanets in the habitable size range, it is fair to assume they are all the same for now. In ignorance, we assume mediocrity. That's the Copernican or mediocrity principle. In which case, again, there are more smaller planets. They produce less calories and they have lower gravity, so organisms can get away with being a bit bigger there. So is the universe full of big aliens? Maybe. I generally distrust Fermi Paradox solutions built entirely on Bayesian statistical reasoning, but the core logic is a lot sounder than most Fermi Paradox solutions I've encountered. Before we go any further, I want to pause for a moment and tighten up what the big alien theory is actually saying, and just importantly, what it is not. When people first hear the name, it's easy to picture a galaxy full of towering giants, and humans as odd little hobbits of the cosmos. That is a fun image, but it's also misleading. Big alien theory was never entirely about height or mass or aliens bumping their heads on the ceilings. At its core, it's about the cost of minds, and the understanding that most of your brain, or an elephant's brain, or a whale's, is for controlling enormous bodies. Only a small bit is for logic, reason, invention, and that's the important part for this theory. Intelligence is expensive. Brains require energy, developmental time, protection, and infrastructure, whether that's biological tissue, social structures, or eventually technology. Bigger organisms tend to have bigger brains. Those tend to require more calories per individual, more territory per individual, and longer childhoods. That creates a trade-off. Fewer individuals spread farther apart, taking longer to mature. So when we talk about big aliens, what we really mean is expensive aliens, species where each thinking individual represents a large investment of planetary resources. And when intelligence is expensive, population density matters a lot. This is where the statistical part comes in. If the universe produces many intelligent species, but most of them are relatively low-density civilizations, because of their bodies, brains, or lifespans being costly, then a randomly selected individual is more likely to come from a civilization where intelligence is cheap enough to support a lot of people. That doesn't make us special or superior, it just makes us more numerous. And we discussed concepts like this, such as the doomsday argument, more in our recent episode on the anthropic principle, which could explain that math and thinking a little bit better. But that distinction matters because big alien theory is often misunderstood as a claim about who's smartest or who wins. It isn't. It's a claim about who's most common at the moment when technology first starts to matter. And that leads to an important limitation. Big alien theory mostly applies to the starting line of technological civilization, not necessarily to what happens afterward. Once a species develops technology, biology stops being destiny. Energy can be concentrated, cognition can be extended, lifespans can stretch, and intelligence can be decoupled from the size and shape of a natural body. Think an uploaded human mind on a very compact computer, or alternatively into a giant spaceship that they ran basically as their body. A civilization that survives long enough probably does not stay bound to the evolutionary constraints that shaped its ancestors. That is one reason I'm cautious about treating this, or any, purely statistical argument as a complete solution to the Fermi Paradox. Bayesian reasoning can tell us what's likely on average, but doesn't explain causes, mechanisms, or histories. It can't suggest why something might be rare, without explaining why it stays rare. So the right way to read big alien theory is not the universe is full of giants, or humans are unusually small, or even this explains why we don't see aliens. It's this. The conditions that make intelligence common are not necessarily the same conditions that make civilization easy, and that means the universe could be full of intelligent life that simply takes longer to cross the threshold into cities, science, and technology, or never does, or does so but in ways that look nothing like our own. With that clarified, we can now talk about what civilizations made of much larger or much rarer beings might actually look like, and whether size ends up being a handicap, an advantage, or something technology eventually renders irrelevant. But one reason I wanted to bring IQ into this is to remember that scientific and technological progress is only directly tied to population if we assume you get X amount of output per person. We do not. One of the reasons I criticize concepts like technological singularity is it assumes we are inherently making exponential faster gains in knowledge. There's nothing inherent about it. We can support more people with more technology, and more of them are free to do things besides food production. Our civilization has come to view that as pretty awesome, and encourages people to be educated and particularly go be scientists and engineers, or to invest money into funding those works. Even ignoring the Flynn effect, which says IQ on average has been rising globally and sharply, we just have a bigger pool of people willing and able to do research. Whereas if you look at, say, 17th century England, when Isaac Newton was pushing the boundaries, the population of all England was about 1,000th what it is now, for Earth entire, and was one of the relatively few places where science was being done in any major way. The literacy rate in that time and place was rising very rapidly too, to about half the adult population by the end of Newton's life, which tends to imply almost everyone with a 130 plus IQ was probably literate, with some outliers, and that wasn't unique to England and more than the norm for the developing world shortly after, which is probably why it was so fast developing. Suddenly almost everyone with a higher IQ could be accessed to start pushing that forward, and a large fraction of those so inclined were able to in some fashion. Our brains hadn't really changed, and in truth our population hadn't much either. It was about 20 times higher at the end of the 20th century than the 1st century AD, but it didn't rise that much between the 1st century and the 15th, then began rising though didn't explode until the 19th and 20th centuries. That's not a period that happened in isolation, but there is a reason the movable type printing press is hailed as the greatest invention of the last millennia, and that the number of scientists shot up rapidly. But we need to be mindful that while scientists need to eat and need people making their equipment and funding their work, it is the total number of productive scientists and inventors, emphasis on productive, not the total number of people, that determines how much science is getting done. Tons of people lived in prior times, and a lot of them were quite smart. Now contrast that and let us look at an extreme case like the fictional aliens, the Zentradi. Depending on the source, the average 30 to 50 feet or 9 to 15 meters tall. They are humanoid, so we assume they scale up in mass, and calorie count. For simplicity, they could be a couple hundred times more massive than us and eat a like amount of food, and that means have a much tinier population, perhaps a few million on a world of them at the dawn of science. As mentioned earlier, they were engineered, but never mind for now. If their IQ was the same, then it's very likely they never built anything bigger than a small village, because they would need so much land to hunt and gather from, or even to farm if they got to that level of tech. But what if they had the same brain format as us? Would they be a couple hundred times bigger of brain? Shouldn't we assume that means a decent chance they have a higher IQ than 100 on average? And again, by our earlier reasoning, even a population with the same distribution of IQ as us, but with a normal just a bit higher, might be getting more science done than us with a tiny fraction of the population. You might have some planet where giant kraken grow constantly bigger and smarter over time, so you've got billions of them in the sea, but only a million as big as you or me, and just a couple hundred ancient ones of Cthulhu-esque proportions, older than dirt, and each smarter than Einstein, and by a wide margin. They may have no ability to go on land and talk to each other only by threatening sonar bellows, but given time and boredom, they might occasionally interrupt those for existential discussion on the nature of the mind, or their growing interest in natural philosophy and experimentation. As uphill a fight as they might have to achieve technology with a couple hundred leviathans who cannot work on land with fire or chemistry, if they have functioning brains bigger than an entire elephant, they might get the job done. How many super geniuses does it take to invent a light bulb? So too, elephants don't have much in the way of natural predators, especially as a herd. You'll sometimes have a crocodile attack a young elephant that comes to drink, and lions have been known to dogpile small or sick elephants when prey is scarce, but not many want to mess with an elephant. And elephants, with bigger size and bigger brains too, would seem a potentially great example of the big aliens that Simpson thinks might be the norm in the universe. We tend to think of the dominant life form on a planet as predators. It's very common in science fiction, But the only actual example we have of a technological species is humans, and our status as a predator in a relationship with predators is weird. For one thing, we bred pets out of felines and canines, two of the major groups of powerful land predators. Our domestication of animals in general is weird, and so is stuff like us not having fur all over our bodies, and wearing other critters' skins. Fire certainly changed us, long before even pottery and metal. We are probably genetically predisposed to be pyromaniacs by now, and our teeth, intestines, and general digestive system are pretty weird these days, likely on account of switching to more meat and cooking it. Always a good reminder that when you're contemplating the origins of intelligent aliens, that humans really are pretty freaky. Also a good reminder that while natural selection certainly still applies, the more brains and technology critters get, the more that's going to alter them. As mentioned a moment ago, we are pretty sure our intestines got shorter from being able to eat cooked meat, which is easier to digest than uncooked plants. Anything that alters diet and improves available energy or energy density to an organism can alter brains too, as they take a lot of fuel. A lot of herbivores we use as livestock will take the same number of bites a day. How calorie dense each bite is becomes important for their fodder. But this is another interesting pair of takes to close out on. First, technological civilizations might tend to grow more energy efficient too, as we looked at in our episodes on cyborg civilizations and transcendence last year. A planet might support 1 trillion humans, but 10 trillion cyborgs or a quadrillion uploaded minds on a computer chip instead. Even if future solar systems were settled fairly evenly by those wanting to be regular folks on terraformed planets, those wanting to stay human and yet build Dyson swarms, and those seeking some hyper-efficient cyborg or uploaded existence, a random person selected from that broader civilization would almost certainly not be one like you or I or from a terraformed and Earth-like planet. For all there might be 1 billion such planets, each with a few billion more or less modern humans on them, they would outnumber us billions to 1, yet still be dwarfed by all those folks living on megastructures or in some sort of post-human state. Unless instead the trend is to become a big alien. I was reminded while writing this that humans are bigger than we used to be, both in modern context and when compared to our earlier proto-human ancestors. Some might argue we bred for size. I would guess so, but I'm not sure the data supports that. But by default, bigger is better tends to be true. Could that lead to us becoming giants in the future? Not necessarily Zentradi style, or like those librarians from House of Suns, let alone the Celestials from Marvel that are 5 miles tall. A humanoid form doesn't really work well at such scales, and a high-tech society could probably grow someone an enormous brain the size of a house, while having them keep a normal-sized modern body that was essentially the avatar they interacted with. Most of your brain in that body is dedicated to serving as an interface to your wider intellect, and as the nominal capital of your personal civilization, which might have millions of subcomponents forming your individual mind. You become more like a cloud intelligence rooted to a human body rather than something you or I might find physically grotesque. Though as we looked at in post-human pathways, with very long timelines to change what is considered normal or grotesque, that's on the table too. See Gene Wolfe's Book of the New Sun for some examples of the latter. The point of technology is to open doors so you can choose which to step through and when, so there is likely to be a post-human expansion option most folks would find appealing over long times, especially as they got more normal. As is, the more time I interact with modern AI, the less worried I am about super intelligent AI replacing us, and the more I wonder when I and others just start getting a basic interface with one better than a keyboard that starts the slow and varied blur between a person and their robo-assistants, so they start becoming like peripheral brain lobes. I don't think there's going to be some murderous battle for supremacy where an AI or a handful of them or post-humans try to wipe each other out for sole access to our entire sun to power themselves as a Matryoshka brain. There is something monomaniacal and pathological about that which never struck me as something a sane person would want to do, and while smart folks can certainly be crazy, I've also never bought the idea that getting smart makes you go nuts. But I also can't think of any particular reason a sane individual would reject simply becoming smarter or faster of mind. Many might not be interested, but many would, and then it's just a question of if the method or process is viewed as revolting or fundamentally altering them beyond something they'd be comfortable with, or essentially erase their identity. Superintelligence that requires the personality equivalent of suicide won't appeal to many. Technology's job is to give us options to avoid that, so given time, I think we or some alien would find a way to make their mind bigger that they were comfortable with and that many embraced. Probably several different methods where one or more was okay to a given person, and most had at least one they would use. Even if it were just for speed superintelligence, which is where the mind merely thinks and experiences faster, so as to let you live in a de facto time bubble of a virtual world where a day passes inside for every minute outside. We tend to think of that as involving a lot of miniaturization and microcircuitry, but at some point you make someone smarter by making them bigger. You also make them safer that way too, because the elephant and the blue whale have little to fear from predators, and a person who still enjoys looking and feeling human might still opt to have the wider part of their mind be physically contained as several redundant backups inside an armored vault that could survive a nuclear strike, and whose effective halt was multiple redundant nuclear fusion reactors with millions of years of fuel stored on site. That could be your future even while your day-to-day reality and experience was just like now, same as you don't really think of yourself as a big dendritic network of billions of squishy neurons, or your body as basically a digestive tract that evolves skeletons, muscles, and brains around it to make it easier to push material into that digestive tract. Both are fairly disgusting when you think about it, so various scenarios for us are some aliens getting bigger by growing our physical bodies larger, or transferring to giant brains in vats or computers in onboard stations is probably not that big a stretch. This might go the scale of a single mind per star system or even galaxy, as some compacted birch planet of a mind. Indeed, you might get plenty of those even if it wasn't the norm. My hunch is that social species are about the only kind that get technology, though the form and degree of how social they are might vary, and I don't think that would get abandoned much. So I think we might see bigger aliens, maybe even Zentradi big, or folks who wore whole living mile-long spaceships, but even then you might have quadrillions of those folks, or ships, comfortably sharing a single solar system where they could chat more or less real time to each other. Although faster thinking makes signal lag feel longer. In the end though, while there might be some trends or preferred sizes, I think you will see a large variety of options in the future, not just big ones, and probably a higher frequency of small options for the same reason there's more small planets and more small organisms. So while there might be some big aliens out there for us to encounter, possibly whole planets of folks stuck somewhere between smart, pre-technological elephant and Neanderthal, I don't think big aliens will turn out to be the majority of what we encounter, or one day become. So, where does all of this leave us? I've been reflecting on that a bit since I originally wrote this episode about a year and a half back, and I feel there are parts of the idea I like, maybe as a partial Fermi Paradox middle-era filter, but it's just got too many problems on the back end to be a strong filter. Does big alien theory actually explain where everyone is? Maybe, but only in a very narrow sense. What it really tells us is that intelligence and civilization are not the same problem. Intelligence can arise under many conditions. Civilization, especially technological civilization, seems to require a very specific combination of population density, energy surplus, and communication speed. Change any one of those, and progress can slow to a crawl. A species made of very large, long-lived beings might be intelligent for millions of years, without ever building cities, not because they are incapable, but because the economics never quite line up. Too few individuals, too much distance, too much time between generations. Not failure, just friction. And that matters for the Fermi Paradox, because we are not looking for intelligence, we're looking for technology that spreads. Once technology does emerge though, big alien theory rapidly stops applying, albeit on timelines that might still be rather long by our standards. You might breed toward a smaller body-to-brain ratio, or adopt technological augmentation. Bodies stop being the limiting factor, minds can be extended, duplicated, miniaturized, or distributed. At that point, whether a species started out small or large becomes mostly irrelevant. History, culture, and choice take over. Which means big alien theory works best as a middle filter, not a permanent answer. It suggests a galaxy that may contain plenty of intelligent life that never quite crosses the threshold into loud, expansive, technological civilization, and a much smaller number that do, and once a civilization does cross that threshold, it likely stops looking anything like its biological ancestors anyway. We really do not resemble other primates that much, especially in ways that really matter. So if the universe feels quiet, that does not require extinction, impossibility, or cosmic loneliness. It may simply be that most minds never reach the phase we're tuned to notice, and those that do not stay there for very long. And as for us, well, we might be early, we might be unusual, and we might just be one of the few species whose biology made civilization cheap enough to get started.